Welcome to our deep dive into the world of europium.
Europium.
Now, europium might not be like a household name,
Right.
but it's actually in something you probably use every day, like euro banknotes or certain types of screens.
That's right. It's one of those elements that quietly powers a lot of modern technology.
Yeah.
And for this deep dive,
Yeah.
you've given us quite the collection of sources,
Yeah.
articles, research papers,
Yeah.
even a podcast transcript.
Okay, so let's unpack this.
Sure.
First things first, what is europium exactly?
Europium is a silvery white metal that belongs to a group called the lanthanides.
Oh,
It's
yeah.
way down there on that quirky bottom row of the periodic table.
Right.
Its atomic number is 63,
Okay.
and it was discovered in 1901 by a French chemist named Eugène Anatole de Marseille.
And as you might have guessed, it's named after Europe.
Exactly.
But here's where it gets interesting.
Okay.
Europium has some pretty unusual properties for a metal.
Yeah.
I mean, we usually think of metals as being strong and hard.
Right.
Right.
Exactly. But europium breaks the mold.
Yeah.
It's incredibly soft.
Okay.
You could actually cut it with a knife.
Hold on, a metal that soft.
Uh-huh.
What are the implications of that? Does it make it difficult to use in applications?
That's a great question.
Yeah.
Its softness does limit some applications where strength is required,
Right.
but it also makes it easier to work with in certain situations.
Okay.
For instance,
Yeah.
its softness and malleability could be advantageous in specialized alloys or coatings where flexibility is desired.
Interesting. So it's all about finding the right application for its unique properties.
Exactly.
What else makes europium stand out?
Well, it's also the least dense of all the lanthanides,
Ah.
meaning it's surprisingly lightweight for its size.
So we've got a soft, lightweight metal.
Yes.
What else?
It's also highly reactive.
Okay.
It tarnishes quickly in air
Uh-huh.
and reacts with water in a pretty dramatic way,
Uh-huh.
kind of like calcium does.
Oh, right. Like
Yeah.
that fizzing and bubbling you see when you drop calcium into water?
Exactly. It's a similar reaction with europium.
Okay, so it's soft, lightweight,
Yeah.
and reactive.
Uh-huh.
Anything else that sets it apart from the other lanthanides?
Here's where it gets even more interesting.
Okay.
Europium can exist in two different oxidation states,
Okay.
+3 and +2.
Okay.
Most lanthanides prefer the +3 state,
Uh-huh.
but europium can comfortably exist in both.
Okay. Break that down for me a bit.
So-
What does it mean to have different oxidation states, and why is that significant for europium?
Think of oxidation states like this.
Okay.
They describe how many electrons an atom has lost or gained.
Right.
Most lanthanides lose 3 electrons, giving them a +3 charge.
Mm-hmm.
Europium can do that too,
Yeah.
but can also lose just 2 electrons,
Okay.
giving it a +2 charge. And this ability to switch between these states
Yeah.
makes it behave differently in different situations.
So it's like europium has a dual personality, which makes it more versatile.
Exactly.
Okay.
And in its +2 state,
Hmm.
europium behaves a lot like barium,
Okay.
which is in a completely different group on the periodic table.
That's fascinating. It's like it has this hidden connection to another element.
Right.
And speaking of connections, you mentioned earlier that europium is used in euro banknotes.
Yes.
How does that work?
Well, one of the things europium is most famous for is its bright red glow when used in phosphors.
Okay.
This glow is a key security feature in euro banknotes.
Mm-hmm.
Under UV light, a genuine euro will light up with this telltale red glow thanks to europium.
So it's like a secret code embedded in the banknote.
Precisely.
Interesting.
And this same red glow makes it useful in other applications too.
Okay.
Remember those older CRT televisions?
Hmm.
Europium was essential for creating those vibrant red pixels.
So that's why you said europium is probably something I use every day.
Exactly.
It's literally lighting up our world. But how did we even discover this fascinating element?
That's a story of scientific dedication and a bit of luck.
Okay.
Remember Eugène Anatole de Marseille, the chemist who discovered europium?
Yeah.
Well, he was actually working with another lanthanide called samarium when he stumbled upon it.
So he wasn't even looking for europium.
Not specifically.
Wow.
He was trying to purify samarium,
Okay.
which was a painstaking process involving repeated crystallizations.
Oh, wow.
It was during this process that he noticed some unusual spectral lines that didn't match up with samarium.
Wait, back up a second.
Sure.
What are spectral lines?
Okay.
And how did they lead him to europium?
Imagine each element has its own unique fingerprint,
Uh-huh.
but instead of swirls and ridges, it's a pattern of lines of light.
Right.
These are called spectral lines.
Okay.
When de Marseille was analyzing his samarium sample, he saw extra lines that shouldn't have been there.
Huh.
It was like finding an unexpected fingerprint at a crime scene. These extra lines were the clue that pointed to the existence of a new element.
So he basically stumbled upon a hidden element while meticulously studying another one.
Yeah,
That's incredible.
it is.
But did anyone suspect europium existed before de Marsay's discovery?
Actually, yes.
Oh,
There were hints.
okay.
Another scientist, William Crookes, had observed similar spectral lines years earlier while experimenting with cathode ray tubes,
Right?
which were the precursors to our modern TVs.
Wow.
But he couldn't isolate the source of those lines.
Mm-hmm.
It was de Marsay's meticulous work with samarium that finally led to the isolation and identification of europium.
It's amazing how these early discoveries often build upon each other, like pieces of a puzzle gradually coming together.
Right.
So we've gone from hidden spectral lines to a versatile element that glows, has a secret connection to barium,
Right.
and is used in everything from banknotes to televisions.
Yes.
What else can you tell me about europium?
Well, there's a bit of a mystery surrounding europium's distribution in the Earth's crust.
Ooh, a mystery.
Uh-huh.
I'm intrigued. Tell me more.
Yeah. So there's mystery about europium's distribution.
Right, and you said it has something to do with how europium is distributed in the Earth's crust.
Exactly. You see, when scientists analyze the composition of certain minerals, they find that the concentration of europium is lower than expected.
Lower than expected. What does that mean exactly?
Well, based on europium's abundance in the universe, we should find it in certain rocks and minerals at a predictable level.
Okay.
But in some cases, it's significantly less abundant than it should be. It's like some of it has mysteriously vanished.
That is strange. What could explain this missing europium?
Remember how we talked about europium's ability to exist in two different oxidation states?
Yeah.
+3 and +2?
Yeah, it's two faces, right?
Exactly. Well, it turns out that this ability plays a key role in the europium anomaly. You see, most other lanthanides stick to their +3 oxidation state and tend to form similar types of compounds, which get incorporated into certain minerals.
Okay.
But europium in its +2 state behaves differently.
So because it can switch to this +2 state, it ends up in different minerals than the other lanthanides.
Precisely. It's like europium decided to join a different rock band while the rest of the lanthanides formed their own group.
That's a great analogy, but why should we care about this europium anomaly? What's the significance of it?
It's actually a powerful tool for geologists. By analyzing the distribution of europium in rocks, they can gain insights into the conditions under which those rocks formed millions, even billions of years ago.
So it's like a geological detective story.
Exactly. The Europium anomaly helps us understand the history of our planet, from the formation of continents to the evolution of the oceans.
That's incredible. It's amazing how something so seemingly small, like the concentration of one element, can reveal so much about our planet's path.
It's a reminder that even tiny variations can have significant implications. But speaking of europium's impact, did you know that it's even connected to the word fluorescence?
Wait, really? Tell me more about that.
Well, it all starts with a mineral called fluorite. You might know it as those beautiful, colorful crystals that sometimes glow under UV light.
Oh, yeah, I've seen those in museums. They're stunning.
Some types of fluorite contain divalent europium, which gives them that characteristic blue glow. And it was this glow in fluorite that first led scientists to recognize the phenomenon of fluorescence.
So they named fluorescence after fluorite, and fluorite owes its glow to europium. That's amazing. It's like europium is secretly behind the scenes making things glow.
It is, and this brings us to another fascinating chapter in europium's story. It's purification and the key role played by a chemist named Herbert Newby McCoy.
Okay, let's dive into that. What was the challenge in purifying europium?
In the early 20th century, shortly after europium was discovered, scientists were eager to study its properties and potential applications. But there was a problem. It was incredibly difficult to separate from other rare earth elements.
Because it was so similar to them.
Exactly. The traditional methods of separation were time-consuming and inefficient.
So they needed a new approach, and that's where McCoy comes in.
Precisely. McCoy realized that europium's unique ability to exist in both the +2 and +3 oxidation states could be the key to its purification.
Ah, I see he used its two faces to his advantage. How did he do that?
He developed a method that exploited the difference in reactivity between divalent and trivalent europium. By carefully controlling the conditions, he could selectively reduce europium to its +2 state, separating it from the other lanthanides that remained in their +3 state.
So he created a chemical filter that could specifically target europium.
Exactly. It was a groundbreaking technique that made it possible to obtain much larger quantities of pure europium, opening up new avenues for research and development.
So McCoy's work was crucial in making europium available for the many applications we know today. That's a fantastic contribution.
It is. And his work paved the way for others to explore europium's potential even further. Now, speaking of applications, let's shift gears and look at what's on the horizon for this versatile element.
I'm ready. From what I've gathered, europium is poised to play an even bigger role in the future of technology. What can you tell me about that? We've explored europium's past, from its discovery
Right.
to its unusual properties and even its geological mysteries.
Uh-huh.
Now let's take a look at what the future holds for this versatile element.
Yeah,
I understand it has the potential to play a role in some cutting-edge technologies.
absolutely. One area where europium is already making a difference is in energy-efficient lighting.
Okay.
You're probably familiar with compact fluorescent light bulbs, right?
Yeah, those curly bulbs that are supposed to be better for the environment.
Exactly. They're more energy efficient than traditional incandescent bulbs,
Mm-hmm.
but they still rely on mercury,
Right.
which is a significant environmental concern.
Right. I've heard about the dangers of mercury. So how does europium fit into this?
Researchers are looking for ways to create mercury-free alternatives.
Okay.
And europium is a key player in that effort.
Huh?
Europium-doped phosphors can be used in a new generation of LEDs,
Yeah.
producing a brighter, more natural-looking light without the need for mercury.
So europium could help us move towards safer and more sustainable lighting options.
Exactly.
That's fantastic. What other applications are on the horizon?
Well, security is a big one.
Okay.
We already talked about how europium's red glow is used in euro banknotes to prevent counterfeiting.
Right. The secret code embedded in the money.
Exactly. And this same principle can be applied to a wide range of products.
Okay.
Imagine inks and coatings that change color or emit a specific glow when exposed to certain types of light.
That's fascinating. What kind of products could benefit from this?
It could be used to protect valuable documents, pharmaceuticals, luxury goods,
Wow.
even food products to prevent fraud and ensure authenticity.
So we could see europium playing a bigger role in protecting our products and information. That's reassuring. But you mentioned cutting-edge technologies. What about those?
Now, this is where it gets really interesting.
Yeah.
Europium is being explored for its potential in the development of quantum computers.
Quantum computers, that sounds incredibly advanced.
It is. Quantum computers are still in their early stages of development,
Mm-hmm.
but they have the potential to revolutionize fields like medicine materials, science, and artificial intelligence.
Okay, but how does europium fit into this? What makes it special for quantum computing?
It comes down to those unique quantum properties we've been discussing.
Okay.
Certain europium compounds can exist in multiple states at the same time, which is a concept called superposition.
Multiple states at the same time? I'm having trouble wrapping my head around that.
Think of it like a coin spinning in the air.
Okay.
Until it lands, it's both heads and tails simultaneously.
Right.
Europium ions can do something similar on a quantum level.
So they can process information in a way that's completely different from our current computers?
Exactly. This allows for massively parallel processing, meaning quantum computers could perform calculations much faster and more efficiently than traditional computers.
Wow. That's mind-boggling.
Yeah. So while europium is already quietly powering things like our screens and lighting it, it could also be a key player in the future of computing.
Absolutely. It's a fascinating example of how an element that was once a scientific curiosity is now shaping the future of technology.
We've covered a lot of ground in this deep dive.
Yeah.
From its unusual properties and surprising connections to other elements,
Right?
to its potential in everything from sustainable lighting to quantum computing.
It really is a versatile element.
Europium has turned out to be far more fascinating and impactful than I ever imagined.
It's a testament to the power of scientific exploration and the unexpected journeys that can unfold when we delve into the hidden world of the elements.
And there you have it, folks. Our deep dive into the world of europium comes to an end.
I hope you enjoyed it.
Hopefully you found it as enlightening as we did. The next time you encounter a red glow, a euro banknote, or even hear about the latest advances in quantum computing, remember europium, the element that quietly powers our world and holds so much potential for the future.
Until our next deep dive, keep exploring, keep questioning, and keep that sense of wonder alive.